So I guess I would just start with like a review of last time that we were talking about support vector machine, right? So SVM here. So just a quick review what we have last time. So the idea of SVM again is that we are still trying to look for a linear classifier. Basically, we um have a projection of like we have X here, and we are trying to project into like some direction like this W here to be precise. So the ones we projected in this way, here like we can separate. For example, in this case, we have like one of this is cat class, this is not cat. Then we can easily separate these points such that like, as long as Wx minus b is bigger than 1, or actually bigger than 0, we will decide that it's a cat. When it's less than 1, we decide it's not cat. So, and of course, the way we select W is such that we want to maximize this gap here. And that's basically what support vector machine is doing. And why it's called support vector machine? Because the point that is like exactly, or like the sample points that is exactly at the boundary of the gap is known as the support vector. Um, and last time we showed that like will be the same as trying to solve this optimization problem with like minimizing W square, such that we want to have all the data points satisfy this constraint, right? Basically, yi are the labels. So on the positive side, like I have yi is equal to +1, and the negative side, I will have like yi equal to -1. So then uh we want to have like all the points, so therefore like every point like on this side here, it should have like label is +1, so multiplied by this guy here should be bigger than equal to 1. And also like for all these points here, it should be less than equal to -1. Wx minus b should be less than equal to -1. So uh, and the label is -1. So therefore, like again, if we multiply them together, it will be less than 1 as well. So, sorry, it will be bigger than equal to 1 as well. So then we have this start with this problem. Then we say, okay, we can. This is a constraint optimization problem, but we can absorb the constraint with Lagrange multiplier. So I have actually how many constraints I have? If there's like n data points here, I will have n constraints here. So I can all absorb that like with a Lagrange with each of them, if each of the constraint with one Lagrange multiplier. So I have like n Lagrange multipliers alpha I here. So I have this modify or augment the like objective function. Now it's like kind of like unconstrained one, not precise unconstrained, because I also have I need alpha I is bigger than equal to 0. And this looks a little bit kind of like increase the complexity of the problem, but it's not. Uh, the trick is like immediately you can try to uh, kind of like solve, instead of this known as the primal problem, we're trying to solve the dual problem here. And the dual problem just swap the minimization and maximization order. So we'll start doing minimization first. So if we try to do minimization first, now this is an unconstrained problem, just in terms of variables W and B. So from the first class of calculus, we can just take derivative or like really the gradient of W and B. Then if we try to solve that, uh, it and we will get something like the solution for this guy will be equal to something like this. So instead, we will have like a problem like trying to now maximize over alpha I, and I should have like the sum of this objective function here. And we said like this is actually this dual problem is easier to solve because of course I have this constraint here. This constraint is what we have originally. Where is this constraint from? Um, yeah, this constraint I think is coming from like solving like taking derivative for b equal to 0. Yeah, if we take b equal to 0, then I have yeah, I only have these terms. I have b, right? So I take with derivative equal to b. So I have this guy here. So I have this additional condition here. So, but we said like this thing is actually quite easy to solve like uh, numerically, because we can consider for each of the i's here, we can fix like if I have n i's, n alpha i's here, I can fix like n minus two of them. I'm only take two of them. And then if I let two of them like to be free, but like I have one equation here, right? So therefore, like actually I will only have like one variable in this case. So for that one variable, you look at this, is just a quadratic equation, right? You can find the solution like right away. So analytically, and then we can hop to another pair of alphas, and then I will iterate, continue to do that. Eventually, we'll solve for alphas. So that's basically what where we were last time, and note that like we also mentioned that there's a complementary slackless condition has to be satisfied whenever we add a Lagrange multiplier term to the original objective function. For the optimal solution there, this augmented term should be equal to zero. You can okay, you can very easy to argue. I'm not going through this again, so you can go back to our previous lecture to if you forget how we get that. But we have this complementary slackless condition, so therefore like this for all I have this product is equal to zero for the solution for the optimal alpha I and W and B. So therefore, like when you see that like when alpha I or I should say like whenever like this is non-zero, that's the case when I'm outside this boundary. So this is like the boundary here, like we'll have Wxi minus b is equal to 1, right? So therefore, like anywhere outside these two boundaries, or like this boundary here, I will have like this will be non-zero. So this is non-zero. It implies that alpha I will be zero in those places. And so therefore, like actually you will have like not a lot of support vector. You only have like quite a few support vectors as you can visualize that. And also like only for these places, alpha I will be non-zero. So therefore, most of the alpha I will be equal to zero. And that's the things, that's the feature is desirable, because in practice, how do I evaluate new input here to classify whether say like an image is a cat or not cat? It'll be like based on the W that we calculated. Oh, actually I didn't put in the W here. Okay, the optimum W is equal to this one here. Again, like this is I solve when we take the partial, pick the gradient of like the objective function here with respect to W, then we get this one here, I believe. And so once we have this optimal alpha I here, the W is equal to that, right? So since like most of the alpha I is actually the optimal alpha I will be 0. So therefore, like this is actually the W is quite nice. So most of the time is like actually in this sum will be 0. We can ignore those. And then what we need to do is when we have new input X, then we will just have to determine whether this is a positive or negative. If it's positive, then it's a cat. If it's negative, then it's not a cat. And then W is here, then we substitute here, right? So then actually this is the real things we need to determine whether it's a cat or not cat. Basically, you go for all the support vectors here, because only the support vectors have alpha i's and non-zero. And then you compute this thing literally, right? Okay, know that this is a scalar, label is scalar. This is a vector, this is a vector, this is actually inner product here, right? The inner product, and then like add with B. So any question? Okay, this is more or less the entire SVM. So just see you guys really completely understand. I guess it's not actually a very easy question. But are you sure you are no questions? Like I'm going to ask a maybe a difficult questions in terms of like how much you understand. I mean like if you have any questions, please ask. So okay, hearing none. So let's see. Like what how okay. I have this thing right here. So what is B then? However, so what is B? I don't know what's B yet. So how do I compute? How do I determine B? I you don't need to okay. You don't need to just like write down the equations. But can you explain that in a sentence? How do I determine B? Or maybe I let me pull this equation up. Then you can, or maybe I just let's see. So you can see everything on like one page. Oops. Yes. Okay. So my question again, like, so I know that like, okay, when I actually evaluate, right here, I know how to what is B, what is W. W is this guy, right? W is this guy here, and I know how to solve for alpha. Alpha can be solved as I mentioned here, right? I can solve for alpha, but here I didn't mention how to solve for B yet. And in terms of evaluation, I need to know what is B. So how do I someone have an answer? Let me yeah. Uh, anyone else? Uh actually you what I mean is you don't need to yeah get into the math a lot. Uh yes, it's the bias, but what is the bias? Let's say like again like we have this. So what is the bias? Like we solve the alpha now, right? We solve alpha. Uh B is the line in x2. Oh, where is x2? You mean here, right? Is that this one? Yeah. Or like no, what is x2? Let me you, yes, actually very close. Can you get even more precise? Like um but how do I know the line? Like how to know which one is the line? Yeah. Well, think of you when you have high dimensional points, or you have these high dimensional points, like you cannot visualize that because like here like we make it just like for the ease of exposition, like this is showing like 2D, right? But in practice, actually, X should be a high dimensional vectors, maybe an image, like I say 100 by 100, then like X is actually a 10,000 dimension vector. And then like what we have like here is like we solve for, we're able to solve for like alphas, right? We are able to solve for alphas. And and we have like maybe like 1,000 data points here, or 1,000 data points here. and I have like the dimension of x maybe can be like 10,000. I don't know in practice like can be like 10,000. I don't know, very high dimension. I can have n is a 1,000, and then I know what is alphas. That I know the alpha star I know, right? Uh, and for alpha star I know what's W, but okay, I didn't give what is B here. Um, yeah, I didn't put it on the slide also because last time I think it's obvious, but at the same time found that like actually uh, when I asked a student, most students don't know what's the answer. Um, so anyone have like any other like kind of you see my question, right? So like any other attempt here? So okay, let me just say it out. So know that that's we have when we know the alphas again like for only for the support vector you will have alpha is non-zero, right? So therefore like if you have like 1,000 samples here as your training data, you have 1,000 like alphas here. Yes, you can. No, actually, it's not. It's not the distance of the hyperplane, but it's the bias terms to make like this is precisely. For example, if you don't have the white bias, then your margin won't be. I mean, your separation plane won't be here, right? It can be like somewhere else, right? So you need to determine. Okay, add the white bias to say that is cat or non-cat, right? So if you only have the direction here, I know W is here. Then if I don't know the white bias, maybe I set a bias here, then I will classify these guys as cats as well. But that's not I want, right? So I want to set the white bias so that like it will be the separation is white between the middle of uh the gap here, right? Um so again like I have like 1,000 alphas here, but only the alphas are at the boundaries are non-zero. Right? So actually, for all these alphas here, uh, I will have like okay, maybe the for the alpha I is non-zero. That means that the ith sample is actually the support vectors. That means that the xi multiplied by w star minus b equal to 1, or this will be equal to -1 basically. So of course I don't know whether it's 1 or -1, but I have like at least two support vectors, right? So therefore I at least have like two equations. Like some of them will be equal to 1, some of them will be equal to -1. For example, like I have, let's say let me I put it here. Let's say I have like I have alpha 0, alpha 1, alpha 2, alpha, just three of them. They are non-zero. So these are non-zero. They are not equal to 0. So they should be the support vector. And so, and the corresponding like data point like x0, x1, x2 should have like either w star x0 minus b is equal to 1, and I may have like w star x1 minus b. It can be +1 or -1. So I mean like okay, okay, it shouldn't be okay. Let's say let's just ignore this b first. It should be equal to some value, right? It should be like equal to a, let's say, or like equal to d, And then like this other value is equal to D, equal to, one is like D1, one is equal to D2. But it can be only be two values because like they can be either 1 minus B or like -1 minus B. So if I pull all the support vectors here and try some of them, actually I don't need to pull all of them, but they can only take two values. If I take the support vectors and I compute this, it can only take two values. It can be either D1 or D2, and but the D1 will be basically 1 minus B. One of them will be 1 minus B, the other one of them is -1 minus B. So then let's say if I take this get value is like maybe one of this is 3, 5, one of this is 3, and then maybe I have W star x2 is equal to 3 as well. Then I will know what is B, right? Basically, I should have 1 minus B is equal to, let's see, equal to uh, 3. Okay, I'm very bad at, let's see, is that 3 or 5? Okay, and -1 minus B is equal to, yeah, okay. Of course, it should be like this one. It will be 3. Difference is 5, right? So then I should have like B is equal to. I think I'm the other way around will be. Right? So then B will be equal to -3, right? In this case, -2, right? Actually, I think like I'm that's still wrong. Like 5 actually good. 5 and 3. Then I will have this B is equal to -4, right? Yeah, I think so. Yes. So you see my point. So okay, I hopefully this is clear. Um, I, I mean again, the main point is like only for the support vectors will have non-zero alphas. So therefore, you can identify those support vectors and you can consider for those support vectors and compute the inner product with W, with the optimal W. It can only take two values because for all of them, like they can be either here or there. And because we remember like W is like this projection, right? And all the support vectors is lying either on this line here or either lying on this line here. So therefore can only take two values. So then like from this you have like at least get two equations and you can solve for B basically. Yeah. Okay. So that's basically support vector machine. I as I mentioned like last time like uh let's see if I can maybe just go back erase some of this handwriting here. So as Brandon asked the question last time, right? So what if what if we have so basically what if we have some sample like let's say here, maybe somewhere here, I have like a cat sample somewhere here, then there will be some outline that is impossible to create a plane to separate them, right? So what we can do is like instead trying to have this hard um support vector machine, like hard threshold or like hard margin support vector machine, we will create a soft margin one. Soft margin in the sense that like you're allowed to have some leeway to get into some error. So then instead of trying to oh, my mouse is not working. Um, so instead of trying to minimize this guy here, so I will try to let's say have this as a hard constraint. We will try to say minimize a loss. Wait a second. Maybe it's better for me just to copy to here, so I don't need to write it. And my handwriting is horrible. Just wait a sec. So instead, I can solve a problem like this. So you can ignore this one half or whatever. So basically, you see, like it's very similar to the kind of similar to the using the Lagrange multiplier to absorb into the constraint. But I have basically here there's a catch here. I didn't define H here yet. Basically, H is as long as the hinge loss. Let me use a H is a hinge loss. So how to spell that? And will be just simply a very simple like a value function. If after we will discuss more. So it's like this is why H x will be just equal to maximum of COMX. So if like x is like bigger than 0, then will be just x itself. When it's like less than 0, then will be like equal to 0. So then now if you look at this one here, what I did is I flip this condition here, right? So like I have like 1 minus this guy here. And when it's negative, so if I have like, let's see, when I have like I want this guy to be bigger than this one, right? I want this one to be bigger than 1 here. So and when I have like this bigger than 1, then it will be these things will be negative, right? So then the loss will be 0. That's exactly what we expected. So on the other hand, like if I have like the condition is violate, that basically this one is less than 1, then I will some additional loss. I'm weighted by C here. So C is some parameters we can modify because it's like some kind of hyperparameter in this case. So then we will, so therefore, like instead of solving again, like for this equation here, we will solve for this now, like for the soft constraint here. And so we can again do a Lagrange multiplier for that way. So if I want to, let me maybe pull this up a little bit. So if I do a Lagrange multiplier, yeah, okay. Actually, the first thing like you may even wonder like why I need to do a Lagrange multiplier. It looks like I have H this a unconstrained problem, right? But the problem like the H here is it's not really a well-defined kind of function here. It's something like it's another like it's tiny kind of you think of a tiny optimization problem here, right? So that's not something we can solve. Like just taking gradient, we don't know how to take gradient inside this argument inside here. So what we can do is that like we'll introduce and kind of like a pseudo or like dumping variable like how to call this? I have forgot. It's a shoot. What's the name for this? Okay, anyone can help me this Greek symbol. I forgot the name for that. I just want to use the same symbol like in my node. Yes, C. Yeah, yes. This is C. Yes, yes. So I can use Ci here as some kind of margin. So I will just replace this problem a little bit. I'll just write it instead of it may be silly if you think of that. I write it as a sum of a Ci, right? And then like 1/2 W square here. Now I have Ci will be equal to 0 if like I have the condition is satisfied. The condition will be like y I w x I minus b is bigger than equal to 0, and then otherwise it will be just equal to itself. So it's equal to oh sorry, like it should be this argument inside. So I'm missing a -1 here. If this is actually this is I want to be less than 0, so this is less than 0. So otherwise it will be just equal to itself. Now it doesn't look like it's helping anything. But then like if I do that, know that like I can change the constraint into this ci bigger than equal to 0 and ci bigger than equal to 1 minus yi wx I minus b. So know that here like I should warn you. I'm thinking like if I can know that like I can do that. By the way, will you question like why I can do that? Like this, know that this is some kind of realization here because the original constraint is like theta I, sorry, ci is either equal to 0 or equal to this guy, right? And of course, it should be bigger than either of them, right? It will be like it will be bigger than this one or bigger than this one here. Then of course, this is a constraint that is uh um actually it's a stronger constraint. Okay, it's a weaker constraint. Uh, originally it has to be either equal to this one or this one, right? But I know that it it will be like equal to the one that's larger than the one that is larger, right? So here I would say like, okay, I will relax the constraint to be bigger than either of them. And I mean, you should actually, when you do something like that, you should ask the question like, is this kind of realization like give you the same solution as before, or like it's it's really doing something reasonable, or like it's actually just realization, but you may get a totally different solution here. So it turns out here it's okay because I remember that C is supposed to be positive because I should be some constant trying um, to scale the penalty. So therefore that C should be positive. So when C is positive, then I know that if I have a solution for that because I'm doing minimization, right? If the optimum solution should satisfy that like Ci should be equal to the lower bound, or basically you'll be either equal to 0 or equal to this guy. So therefore, like it's really totally okay, like to relax constraint to this, and I can be sure that the solution will be exactly the same because C is positive. So let me pull this. Yeah, that's fine. Okay. So then with this, we can do the Lagrange multiplier, right? So instead of like solving this guy with this constraint here, I'm solving like this with these constraints here. So again, I can just apply Lagrange multiplier. So for each of the constraint, I should have a corresponding Lagrange multiplier, and then I should kind of add it to that. So let's say I have like Ci is bigger than equal to 0. I can have a, let's see, what symbol do I use here? Oops. Uh, I can have like a additional kind of Lagrange multiplier Ri in my notes, SCI and sum over all I. And then for this one here also I can have Lagrange and additional Lagrange multiplier, say alpha I, and I will have sum over uh, let's see, uh, Ci minus this guy here. So okay, let me just copy this thing so it's it will look nice. Maybe I even remove my handwritings here first. Okay, so I have now the problem like replaced by this one is that, so I have the new objective function here is like unconstrained, is L. I try to minimize over, so I need to minimize this. And with respect to W, but also like I have also now new W and B, right? But I have introduced a new variables here is a, or actually WB and also CI as well. The CI is the original variable, but I also have like this additional Lagrange multipliers are also like variables, say alpha I. Actually, maybe I should also, right, as last time, like we have minimized original minimizing W, B, and CI, right? I cannot erase this thing, but maybe I can just call this out. And then I have minimax problem, like I have maximizing over alpha I and also like Ri here. Now I can again trying to do a swap of this optimization problem, like I swap that, then over here, then I trying to do again, I can take then okay, this would be like bigger than zero here. But again, I will have some unconstrained optimization over this one here, so I can just use again like gradient, like take the gradient of like with respect to, if I call this L here, take the gradient of L with respect to W and also B and also like CI here, and should set to zero. And so set all to zero, then um it would be okay. I guess maybe I'll just go to a slide here. I think, oh, oops, to pull your chart here. Oh, I don't know why that symbol is a hopefully that okay, let me probably should restart this. Mm. So okay. Now we just mentioned like it was just this is showing like what we had earlier. So we have this new problem like for the soft constraint case, soft margin case, I trying to solve this, then like we can uh absorb this Lagrange multiplier, like with Lagrange multiplier to absorb this constraint, and this constraint. So for this one, I have introduced a new Lagrange multiplier, say this Ri here. And then for this guy, like we have Lagrange multiplier alpha I here. Now then we just say swap the optimization again. Then we take the gradient with respect to like um, XBM CHI, and then we will solve something like again like W, basically with the same expression as we have that earlier. And also take derivative with respect to B. We have this guy like as before, and we all have like take derivative with CI. Then we have a new equation here like this. I mean, such actually everything is very similar to before. And then like the dual problem, like eventually we have something like this if we substitute everything back into the equation. So it will become like trying to maximize alpha actually is more than just yeah, we will have something like this. And also I have alpha I will be uh, will be within the range of like CM0. So it's because from here we have Ri is bigger than equal to 0. But alpha I is also bigger than equal to 0. Therefore, alpha I should be like between like CMC, 0 and C. And also we have this constraint here. So everything will be like more or less similar to before, right? We have like a very similar equation like last time to solve like for alpha. And so we can again like solve it quadratically and find the alpha. And this time like the alpha, again like alpha will have several cases this time. It will be a little bit different than last time. So but you can go for maybe I just roughly mentioned that because we also have this complementary less constraint. Remember that like whenever we add that Lagrange multiplier term here, for the optimum solution, this guy should be equal to 0. So therefore we have this complementary slackness constraint. And earlier we also have like this one is equal to 0. That is like we take derivative over CI, we get this one is equal to 0. So now if we look at different cases here, for example, like for Ri between 0 and C, and then you can argue that okay, this yeah, you can see that like Ri becomes COMC, then alpha I has to become CMCO, right? So I'm not hitting CMCO, and because alpha I is non-zero, so from this complementary slackness constraint, this one will be equal to 0, right? So this guy equal to 0, and also we will have Ci is equal to 0 because our I is non-zero, then Ci is equal to 0. So I'm also Ci equal to 0. So then we have like this is equal to 0, equal to 1. Okay. I'm quite sure like, and we can do the similar stuff that like this. And you can argue like for different condition here. Okay, I just asked a question that see if you can answer from here. I have case A, B, C, 3 cases. Like which one is support vector? Case A, B, or C? Which one is support vector? Uh, okay, I guess I'm not trying to make this uh kind of like a tricky question, but know that like the key here is here. You may be confused with other things. The key is here, right? So after all, it's like all these guys determine whether it's a support vectors, right? So this is like the one hitting the boundary, right? If you remember the always the picture we have, I guess it's always always important, like have the picture in your mind. So when it's equal to a support vector, it's these cases, right? So therefore, like I should have uh, this thing should be equal to either 1 or -1, right? And multiplied by the label is like 1, and 1 or -1 should get back 1. So this is should be the support vector. And now I guess this, if you just have so which one violate which are the outlier? Again, B or C, like because A is a pop vector, only B or C can be the outliers. Like B are the outliers, or like C are the outliers? Yeah, actually, again, it's good to go back to this guy here. This side will be this getting bigger than 1, right? And this will be like this value will be less than -1, right? So either case, like on this side here will be the magnitude will be like bigger than 1. So therefore, like the case that is bigger than 1 is actually not the outlier. The outliers are the one is like here, right? Within this region here. Or like actually it can be even like 1 point get to the other side here. So that should be the case that like that would be less than 1. So if it's like it's yeah. So therefore like actually outliers is case B. So but it's good to know because again after you solve for this all alphas here, if you want to solve the B, you should first like determine which are the support vectors, right? But you know which are the support vectors. Basically, support vectors should have like alpha I between 0 and C. And then from that, we can, again, using the same argument we have before to find this B here. Then from this, yeah, then you are basically done. Then to evaluate, just look at whether you are, yeah, whether you have like this is like for a new X here, for a new X here, then you will just determine whether Wx, the dot product minus B is bigger than 0 or less than 0. So if like bigger than 0, then it's like a this positive class, otherwise the negative class. So okay, let's see.
Professor, I had a
Yes.
quick question.
Yes.
So, Professor, there is no chance of outliers lying beyond like the range, like greater than 1 and less than -1. There are no chance of outliers being present there at all. Like they'll always be in between the range from 1 to -1.
Yeah, it's a very good question. Let's see. I no, actually, no, you can because I be careful. That's a you can all go all the way for this guy here. It's good when you are on this side, right? So you can have outliers all the way, like not just one here. You can go all the way to minus infinity. I'm not sure I explained that. So I think your question is more like what if I have points that go all the way like across here, like all the way here, right? So you can really have that situation. You just have like this here will be even less than -1. Wait, outlier. Yeah, this one is the outlier. Less than 1 is already outlier. But if it go to like -1, it actually reach the other guy's territory, basically.
Right, right.
Yes. Yeah.
Okay.
So okay, I guess that's uh so let's look at well, how about if I have multi-class like SVM multi-class problem? So if I have multiple class, then I want to have like a multi-class SVM. And one way to handle that, like one possible way, may not be the best way, uh, will be like very similar to the soft margin case. But I have like now I have more classes and not just like eh, like at the beginning, if I only have 2 class, then I will have oh, okay. I oh I guess let's see. What when I have 2 cars we have uh, uh I don't know whether it's better or worse to use here. Let's see. A sec. Now I get lost with the oh I didn't copy anything. So okay, I guess it's okay. But this is the remember this is a when I have 1 class here. When I have multi-class, then I can oh actually I have that. I copied that. So I did lots of copy paste just before the class so that it will be a bit easier. So maybe I erase some of this drawing here. So for multiple class, I may extend from the soft margin, like in a very similar way, like to okay, maybe I erase this thing in the middle. I just so you can see the expression is very similar. We can do very similar things. Like now in the one just 2 binary case, 2 classes case, so we basically want this guy to be positive, right? So want to set this thing to be positive, so that like when it's negative, then we will have a loss. Wait, actually the other way around. We want these things to be negative, right? So if it's negative, then doesn't contribute a loss. When it's positive, then it's a loss here. Now here similarly, we can do something very similar. When we have like more than 1 class, let's say if I for each of the sample, let's say I have xi just have 1 training sample here, and let's say the true class is j xi here, the true class is j here. So we want to have the score for all the other guys is less than this guy here, right? Less than the j, the score by the j class, and then like so if this is the case, then like this would be negative, right? If this is bigger than everyone else, then would be negative. That would be nice. And also we can add an additional margin here, add a delta here. Is we want to make sure that it's not just uh, each of the class is less than Sj, each of the score of each of the class is less than Sj, but also is less than Sj uh, my yeah less than Sj minus delta. Did I say something correctly? Let's see. Yes, yeah. We want to we have to, so we want this like let's say this is like one of the class. This is like the score for the true class here is Sj here. So we want this other class to be less than that, but we want to have like maybe you can set a margin, let's say a delta here, so it will be not just less than like Sj, but maybe less than Sj minus delta here. So then we can formulate this problem, then I try to solve that. But if you do that, like by the way, you cannot use a like solve dual problem. I don't think it's, you may try that, but just I didn't try it myself. But my impression is that you cannot solve it as a dual problem, most likely. So, but you can, for example, like do it by brute force. So in that case, you just take it as a optimization problem, like using gradient descent to solve for the optimum score. Of course, I didn't specify the scoring function here, but the scoring function simply can be uh, have forever, whenever you have input x here, you have just a scoring function multiplied by a matrix, basically. So in previously, we have like multiplied by a vector w, or like inner product of w. But in this case, you have like different score for different class, right? So maybe more, let me make it more precise. So let's say x is a feature with like 5 vectors here, five features here. So therefore x have a length 5. Now I can have like s just maybe I have like 3 different classes here. So then I can have like this s here as x is just equal to as a vector here is just equal to this 3 by 5 matrix multiplied by this x here. Then we want to train these parameters here, basically. So, okay, this is just a quick remark for like multi-class. Actually, for scikit-learn or something like that, I think like it's also often like people will implement multi-class SVM by instead using, let's say, one out of others. Like for example, like if I have like 3 classes here, like let's say I have more classes, I have one more classes here. Another way to do that is I can also always say train classifier as a one against many. So for example, I can train one classifier. For example, this is a cat, dog, and bear, let's say. So I can train like cat versus not cat. So I have one class here. And then I can train like dog versus not dog. Then I have another class here. Oh, sorry, another classifier here. And then I can train like bear versus not bear, then another classifier there. So then basically I can just um, kind of combine the result of these 3 binary classifiers to do multi-class classification. So this is another way to do that also. So if you do it like this, of course, you can go back to this classic SVM way to optimize the problem, or to solve the problem. So again, I formulate as a dual problem. You can find this alpha as a very easily, and also like B very easily, and so on and so forth. One more thing I like to mention. Okay, let's see. Maybe I can just use the slides. Let's see if I can just explain it clearly using just the slides alone. So one, maybe I just go back to one of the solution here. Okay, maybe like first of all, like maybe just get a poll here, like how many of you like heard of a low kernel trick? So okay, I guess it's worth like talking about them. I probably like also like I think kernel tree is something like really nice that like probably should spend a little bit time. I probably like okay, like here I can still like say it's a new lecture, but please bear with me. I probably will do one class like maybe next time like on like PCA like yeah that's there's maybe a quite bit stretch for lower levels but only for one class because uh I like okay basically for SVM it by itself is actually not very useful even you allow soft margin because for most data for example if I have data like this I don't care like whether you are doing soft margin. Like let's say this is one class like that, and that's another class like that. Then it's actually it doesn't matter whether like you are doing soft margin, hard margin, or whatever. Like there's simply no way to separate these two classes easily, right? Using just a binary classifier. And SVM, by the way, like it's actually really just a not binary, a linear classifier, right? So SVM is popular and was popular and was useful is really because of the kernel tricks. It's like we don't actually use SVM like directly. We always like apply SVM by first like project. You can think of like okay, this is like uh, intuitively thinking is like we're projecting the feature like x into some high dimensional space. I have 3x here. For example, maybe x is just 5D, like the feature is just 5 dimensional. But I project to very high dimensional, maybe like 500 or like even 5,000, or like it can theoretically to an infinite dimension. Now, when you have like things like project to infinite dimensions, stuff that doesn't necessary to be separable, like, will become separable. Um, and by using that, then if you are applying your support vector machine into high dimensional space, then you can pretty easily like kind of like separate the classes without any problem. So that's the idea. But the problem here is like why they call it trick is like you cannot do this like literally, right? So I cannot really project like to let's say okay 5 dimension maybe 5,000 dimension maybe it's okay but I cannot project to an infinite dimension. I'm hopefully able to process that way. So what happened is like we try to project to a high dimensional base space but we didn't actually do that literally. So the way to do that is that we introduce some kernel function, let's say kx, let's say I have kxy, this is a two features in the original space. I have a kernel function k. This is basically defined as the inner product of this x and y when it projected to a high dimensional space. So, and of course, like this itself, like it's not helping much if like if we're trying to like find the kernel from solving this thing, right? If we go for like each of x and y, I'm trying to define like the kernel as this. I'm trying to find like kxy as actually literally trying to compute this. So the trick here is like we don't actually even compute this. We don't know what is fine. Most of the time, we don't actually care about what is fine. But we define a kernel, and we take the kernel as if it is like a inner product in the high dimensional space of x and y. And for example, a very common kernel when people will use is like you can have any dimension of vectors. I can like xy this kernel kxy as a so-called Gaussian kernel will be like um, the second norm uh, of x and y. Basically, like okay, this is just some pseudo parameter. C here, just some pseudo parameter. It's more or less like the variance of the spread of the distribution here. So then it will have something like if you think of that would be something like x close to y, then this value will be big, otherwise will be small, like decay like exponentially. Um, so if you look at like go back to SVM problem here, we can apply the kernel trick right away. So note that what we have been solving so far is basically solving some alpha from some optimization problem like this, right? And then we will solve for like when we apply that, we need to evaluate this guy, right? Evaluate this guy. Now, the only thing that will change here is that like you see there's an inner product here. So instead of like processing in the original space, we will project to a really high dimensional space. So we are considering phi xi, phi xj instead, right? The inner product of this guy instead. And here also when I evaluate that, like this one will be replaced by like phi xi and phi x. And of course, I said like I I I can replace this inner product using the kernel function, right? We can so and this will be just replaced by basically, let's say if I use the Gaussian kernel, then this guy will be just equal to exponential minus xi minus xj over some, maybe I just say put it 2 here anyway. And then like again here, like will be replaced by something else, right? But I replace by this, it doesn't change anything, right? I can still solve the same problem. Like any I mean what we have been doing so far, like we can still in the same way solve for alphas. And after that, like with alpha star, like we can still like evaluate this like with this guy here. Yeah, so this is like basically that would be like kernel SVM basically. And actually that's almost always like people use like when they say SVM, they actually when they trying to solve a real problem, like it's almost always is like really referring to really, what really they are doing is like the kernel SVM. Otherwise, if they just use a plain SVM, it it won't be very powerful. Yeah. So is that clear here? Uh, I have some time here. So I'm thinking like as I mentioned, like since we talk about kernel tricks here, I want to give another example of using kernel trick. It's like I want to talk about PCA, then I want to say how to generalize using kernel PCA. Um, I probably 5 minutes won't be enough for me to do much. So maybe I just say um, okay, maybe I just give a quick review, like in case I'm not sure like, how many of you are still kind of like remember like eigenvectors, all these things like very much uh, on top of your mind or something. So let's say if I have like I have a matrix, let's say matrix C here, and we say X is an eigenvector, then we have like Cx is equal to lambda x here. And psi x is equal to lambda x. And x in this case will be the eigenvectors. And lambda will be eigenvalue. Um, and by the way, C should be a square matrix. Otherwise, people are kind of like enforcing C a square matrix. And um, um, okay. Let me see like how much you know about or about like um do you let's say like um lambda. By the way, can lambda be a compass? Let's say there's a question like, can lambda be compass? And so I see someone, I'm not sure how many of you are still around or like don't know the answer. In general, like lambda can be compass, but actually in engineering, most of the time, you see we treat lambda as real. And this may be like a little bit more, but it's again, I want to just check you guys for background. So when will lambda be real? Do you know like this may not be uh,
Is it if the eigenvectors are real as well?
uh not necessary actually. Yeah. Actually, by the way, the eigenvector you can make it not real, like because if you have x, it's even x original real. If you make multiply by I, let's say this will be an eigenvector as well because you have c I x is equal to lambda I x, right? This will still satisfy. Yeah. So yeah, that's eigenvector is real only when I see is actually is symmetric. Actually, if you consider C can be complex as well, then C should be so-called Hermitian. Yeah, but let's say that don't worry about it when C is complex. So when C is equal to C transpose equal to C, then I will have lambda is real. And actually to show that on the other hand, like it's easier to show like the Hermitian case. Basically, when C is Hermitian, then lambda is real basically. And Hermitian, this is a symbol for Hermitian. Uh, Hermitian is basically just mean like symmetric. Take the transpose and take the complex conjugate. So this is equal to transpose and then complex conjugate. Um, and and I don't know like whether I can let's see. I may try to show that, like see if I can one. Oh, okay. I want to like show. Okay, but okay. Basically, if you consider that, you probably will get it correctly. So this will be some value here. Okay, let's forget it because I'm over time now. So okay, let me next time maybe give a little bit review or eigenvalue, eigenvectors, and then I talk about PCA, and then I talk about like kernel PCA. So then most likely the lecture afterward, I will start really talk about little lectures. So okay, SVM is still like little lectures. You can think of really simplified little lectures with single little ones. but then we will talk about like networks of neurons for the next class. Okay, so I'll see if you guys have any questions, any uh, um, related to anything. Otherwise, we'll just stop here, basically. So, and yeah. So if you, yeah, just let me know if you have any questions or like pose a question in Discord if necessary. So I will see you guys next week then. Yeah.
See you.
Thank you so much,
Yeah.
Professor.
Bye. Thank you.